The dry winds carried the scent of dust and sweat as ox-drawn wagons groaned their way across the open plains. Every few miles they halted to adjust or grease the wheels. The sound of squeaking and rattling wheels was constant, a reminder of load and friction that wore metal against wood until both gave way. Settlers expected their wagons, sturdy and well-built, to survive the harsh conditions of the frontier. The reality proved different. Wooden wheels and iron axles were ill-suited for daily wear on rough terrain. Constant repairs became routine. Then a farrier named Eli Ward tried something ridiculed, soaking wheel hubs overnight in hot oil. His logbook noted simply, "No rattle, no worry." They didn't yet know that this quiet method would cut breakdowns by half and spread across every western trail for the next 3 decades. The tin trough measured 18 inches long, 6 inches wide, and 4 inches deep. Fabricated from sheet tin by any competent blacksmith, it cost approximately 15 cents in eastern markets during the late 1840s. This unremarkable vessel would become the foundation of a maintenance revolution that kept thousands of wagons moving west. The wagon train had departed Independence, Missouri, 6 weeks earlier. 43 wagons carrying 167 settlers, livestock, and supplies stretched across the prairie in a line that extended nearly half a mile. Every wagon followed the same basic design that had proven adequate on eastern roads: wooden wheels with iron tires, hardwood axles, and oak or hickory spokes. The terrain betrayed those assumptions quickly. Prairie crossings meant dry creek beds with rocks that jarred every joint. Soft soil grabbed at wheels, increasing resistance. Wind-blown sand worked into every bearing surface like grinding compound. The temperature swung 40 degrees between midday heat and pre-dawn cold, expanding and contracting every metal component. Caleb Stevens, a homesteader from Ohio, recorded the damage in his journal. Another day, another wagon wheel failure. It is almost impossible to keep them greased enough for the journey ahead. The typical maintenance routine consumed enormous resources. Each wagon required regreasing every 3rd day. The process demanded removing the wheel, cleaning the axle, applying fresh tallow or lard, and reassembling the components. A single wagon consumed approximately 20 pounds of grease per 100 miles of travel. The grease itself presented problems. Animal fat attracted insects and dust. It thinned in heat and stiffened in cold. It required constant replenishment. Most critically, it provided inadequate protection under the sustained friction of daily travel. Wheel failures multiplied as the journey progressed. Spokes loosened when the wood dried and shrank. Iron tires separated when the wood contracted beneath them. Axles wore grooves that accelerated further damage. Each breakdown delayed the entire train. The question was no longer how to get the wagons moving, but how to keep them moving without constant failure. By the campfire, farrier Eli Ward prepared his evening routine differently than the 42 other wagon owners. He positioned a tin trough beneath his wagon's front axle and filled it with rendered beef tallow, heated until liquid. The wheel hub sat submerged in the hot oil. Settlers watched with skepticism bordering on mockery. Ward had worked as a farrier in Pennsylvania for 12 years before filing for Oregon land. His experience with draft horses and freight wagons had taught him that friction was the enemy of all moving parts. The standard practice of applying grease to the exterior of bearings treated the symptom but ignored the cause. His method involved placing the tin trough so the wheel hub, the wooden cylinder at the wheel center through which the axle passed, sat in hot oil for 6 to 8 hours overnight. The thermal properties of heated oil allowed it to penetrate deep into the wood grain, filling microscopic spaces where friction generated heat and wear. The oil's composition mattered. Ward used beef tallow, rendered from cattle butchered for food. The rendering process removed water and impurities, leaving pure fat that remained stable across temperature ranges typical of prairie travel. Vegetable oils oxidized too quickly. Lard contained too much water. Tallow provided the optimal balance of viscosity, penetration, and stability. The mockery was predictable. Oil on wheels seemed absurd, a waste of time and valuable resources. Settlers ridiculed the idea. One neighbor, John Collins, recorded in his journal, "I am not wasting oil on my wheels. I will stick to grease. It has worked for years." Ward's wagon moved differently the next morning. The characteristic squeak that announced every wagon's movement was absent. The wheels turned smoothly, requiring less effort from the oxen. The difference was subtle, but measurable. The oil had penetrated the hub, creating a reservoir of lubrication that fed the bearing surface continuously as the wheel rotated. The heated application expanded the wood grain slightly, allowing oil to reach areas that surface application could never touch. As the wood cooled and contracted, it trapped the oil inside, creating a long-lasting lubricant supply. Despite mockery, Ward's solution worked. But could it truly make a difference over hundreds of miles of brutal conditions? As Ward continued applying his method nightly, the sound profile of the wagon train changed. 42 wagons still announced their presence with the familiar grinding squeak of wood on metal. One wagon rolled quietly. The contrast became obvious to everyone in the train. Ward's wagon, positioned roughly midway in the formation, moved with an ease that defied explanation to those who hadn't examined his method. The oxen pulling his wagon showed less strain. The wheels maintained their alignment better. The spokes remained tight in their mortises. Other settlers continued with traditional grease application, seeing little improvement despite their efforts. Their wagons still squeaked and struggled under loads. Ward's wagon, by contrast, ran quietly and smoothly with fewer repairs needed. Sarah Hendricks, traveling with her husband and 3 children, recorded her observations in a diary that would later be archived at the Oregon Historical Society. "Ward's wagon runs like it is gliding. Ours are all falling apart. Yesterday we spent 2 hours repairing a spoke that worked loose. Ward passed us without stopping." The technical explanation lay in the oil's behavior under load. When a wheel rotated under the weight of a loaded wagon, tremendous forces compressed the hub against the axle. This compression generated heat through friction. Traditional surface grease liquefied and was squeezed away from the bearing surface, leaving wood directly contacting metal. Ward's oil bath method created a reservoir within the wood itself. As the hub heated during use, the oil became more fluid and migrated to the bearing surface exactly where needed. The process was self-regulating. Increased friction generated heat, which mobilized more oil to reduce that friction. The oil soak also prevented another critical failure mode. Wooden hubs exposed to repeated wetting and drying would crack along the grain. The oil penetration sealed the wood, preventing moisture infiltration that led to rot and structural failure. Ward's wheels showed measurably less wear after 2 weeks of travel. The grooves worn into his axles were shallower than those on comparable wagons. His spokes remained tight without the constant tapping with a wooden mallet that other settlers performed daily. But would Ward's quiet innovation catch on, or would it remain a solitary solution, laughed off by the majority? The settlers' wagons continued to grind and creak through harsh terrain. Every stop was marked by wheel repairs and frequent complaints. Meanwhile, Ward's wagon kept rolling with ease, but many refused to accept his method. The resistance stemmed from multiple sources. The oil itself represented a cost that seemed unnecessary. A gallon of rendered tallow that might be used for cooking or candle making cost approximately 25 cents in eastern markets when available. Using it for wagon maintenance felt like waste to families counting every resource. The method also required discipline that conflicted with the frontier mindset, favoring quick solutions. The axle bath demanded nightly setup and morning cleanup. The trough had to be positioned carefully to avoid spills. The oil had to be heated to the correct temperature, hot enough to penetrate, but not so hot it charred the wood. The process took 30 minutes each evening and another 15 minutes each morning. John Collins's journal documented the skeptical majority position. "I am not wasting oil on my wheels. I will stick to grease. It has worked for years. Ward can spend his time playing with tin dishes if he wants. I will use that time to make miles." Those who resisted continued to face breakdowns. Collins's wagon threw an iron tire on May 8th, requiring 3 hours to repair. His left front wheel developed a wobble on May 11th, when 2 spokes loosened simultaneously. By May 15th, he had consumed 32 pounds of grease, attempting to keep his wheels functional. Ward's wagon, by contrast, required no repairs during the same period. His grease consumption was effectively zero. The oil bath eliminated the need for supplementary lubrication. His oxen showed less fatigue because they pulled a more efficient load. The mathematics of efficiency were undeniable to those who observed carefully. Ward's method consumed approximately 1 quart of tallow every 5 days. The oil could be reheated and reused multiple times before it degraded. Collins's traditional method consumed 6 pounds of grease every 3 days. The grease had to be replaced completely each time. Could Ward's method be the key to longer, more sustainable journeys, or would skepticism and perceived cost keep it from spreading? Ward's wagon continued performing well as others struggled. He began recording detailed data in his logbook: miles traveled, oil consumption, time spent on maintenance, condition of wheels and axles. The numbers told an unambiguous story. From April 28th through May 15th, 18 days of travel covering approximately 240 miles, Ward's wagon required 0 wheel repairs. His oil consumption totaled 1½ gallons of rendered tallow. His maintenance time averaged 45 minutes per day, almost entirely spent on the evening oil bath setup and morning removal. Comparable wagons using traditional methods required an average of 2 significant repairs during the same period. Grease consumption averaged 60 pounds per wagon. Maintenance time exceeded 90 minutes per day when repair time was included. Ward noted in his logbook, "No rattle, no worry. Each mile is easier. Fewer repairs. I have saved time and money. The oxen show less strain. The wheels remain true." The thermal properties of the oil provided benefits beyond simple lubrication. The regular soaking prevented the wood from drying and shrinking, a constant problem in prairie conditions where humidity could drop below 15% during afternoon hours. The oil seal kept moisture out during wet crossings, preventing the rot that plagued unsealed hubs. The method also reduced rust formation on iron components. The oil coating protected the axle and iron tire from oxidation. Rust acted as an abrasive, accelerating wear on both metal and wood. Preventing rust formation meant slower degradation of all components. Ward's record showed another unexpected benefit: spoke retention. The oil penetrating into the hub also reached the mortises where spokes were fitted. This lubrication allowed the joint to move slightly without loosening completely. Traditional dry joints became brittle and failed when shocked by rough terrain. As Ward continued keeping meticulous records, the benefits of his method became increasingly clear. His wheels remained functional for longer periods with fewer issues than any comparable wagon in the train. By mid-May, a few settlers began asking questions. How did the method work? What oil was best? How hot should it be? Could the method be adapted to smaller troughs? Could this simple solution become the standard, or would resistance hold back progress? Word of Ward's success began spreading beyond observation to experimentation. Thomas Harper, a settler from Indiana traveling with his wife and 2 sons, became the first to replicate Ward's method. Harper had watched Ward's routine for 3 weeks with increasing interest. His own wagon had suffered 2 breakdowns in that period: a separated tire that cost 4 hours of labor and a cracked spoke that required replacement using precious spare parts. On May 18th, Harper approached Ward and asked direct questions about the technique. Ward shared information freely, explaining the importance of heat, the ideal oil temperature, the positioning of the trough, and the timing of the soak. Harper fabricated a tin trough from a damaged water container, cutting and reshaping the metal using basic tools. His first attempt was crude but functional. On the evening of May 18th, he positioned the trough under his right front wheel hub and filled it with heated tallow. The results were immediate and dramatic. Harper's wagon, which had been among the loudest in the train, rolled quietly the next morning. The oxen responded to the reduced resistance, moving more freely. The wheel that had been the source of constant concern showed no sign of the looseness that had plagued it. Harper documented his experience in a letter to relatives that was later preserved in family papers. "I was skeptical, but after using the method for 1 week, my wagon's wheels are as smooth as silk. The difference is remarkable. I wish I had started this practice at the beginning of our journey." Other settlers noticed Harper's conversion. The fact that a second wagon now employed the method and showed identical results forced skeptics to reconsider their positions. A few began quiet experiments. They didn't announce their adoption of Ward's method, perhaps to avoid admitting error, but tin troughs began appearing under wheels at evening camps. The distinctive quiet of properly lubricated wheels spread through the train. The adoption wasn't universal. Roughly 1/3 of the wagons continued using traditional methods. But the trend was established. Those who adopted the axle bath method experienced measurably better outcomes than those who didn't. Could the axle bath be the secret to smoother, longer journeys, or would the trials of rough terrain expose flaws in the approach? As Ward's method spread within the wagon train, it also diffused to other travelers through chance encounters at river crossings and trading posts. The informal network of trail communication carried techniques as effectively as it carried news. Samuel Stone operated a small trading post near Fort Laramie where multiple trails converged. Settlers, trappers, traders, and military personnel exchanged information as readily as they exchanged goods. Stone heard about the axle bath method from a settler who had encountered Ward's train at a river crossing in late May. Stone's trading post records, preserved in the Wyoming State Archives, document the rapid spread of the innovation. In early June 1849, he recorded the first sale of tin specifically requested for trough fabrication. By mid-June, he was selling 2 to 3 sheets of tin per week for this purpose, a dramatic increase over previous months when tin sales averaged less than 1 sheet per month. Stone wrote to a supplier in St. Louis, "I have adopted the axle bath method for my own freight wagons, and my wheels are running smoother than ever before. Several customers have requested tin for making troughs. I recommend stocking additional supply." The method spread accelerated because it required no specialized tools or rare materials. Any competent blacksmith could fabricate a trough in less than an hour. The oil was widely available. Rendered animal fat was a common byproduct of frontier food preparation. The technique itself was simple enough that verbal description sufficed for replication. Mechanics and farriers adapted the method to different vehicles and conditions. Some used larger troughs for heavy freight wagons. Others developed smaller versions for hand carts. A few experimented with different oils, testing vegetable oils and mineral oils against animal fats. The core principle remained constant. Sustained lubrication through deep penetration and thermal management produced superior results compared to surface application of grease. By early summer 1849, the axle bath method had spread along hundreds of miles of western trails. Farriers began teaching the technique to customers. Settlers shared information at river crossings and mountain passes. Could this small change lead to widespread adoption across the entire frontier transportation network? A wagon train bound for the Willamette Valley faced the decisive test of Ward's method under the most challenging conditions of the entire westward journey. The crossing of the Blue Mountains in early July exposed every weakness in equipment and technique. The wagon master, Jacob Reeves, documented the journey in reports filed with the Oregon Provisional Government. His train included 53 wagons. Approximately 40% had adopted the axle-bath method, while 60% continued using traditional maintenance. On July 3rd, the train encountered a sudden rainstorm while ascending a steep grade through the mountains. The temperature dropped 20 degrees in 2 hours. Rain turned trail surfaces into mud that clung to wheels and increased resistance dramatically. Traditional wagons struggled immediately. The combination of steep grades, mud, and cold caused grease to stiffen. Several wheels froze completely, requiring emergency repairs. 3 wagons had to be unloaded and partially disassembled to free seized bearings. Wagons using the axle-bath method continued with minimal difficulty. The oil remained fluid at lower temperatures than animal fat grease. The deep penetration meant bearing surfaces stayed lubricated even when exterior moisture washed away surface lubricants. Reeves's report included specific data. Wagons employing the oil bath technique experienced 0 complete failures during the mountain passage. Traditional wagons suffered 11 significant failures, requiring repairs exceeding 2 hours each. The difference in performance was pronounced and consequential. The time differential was stark. The oil bath wagons completed the mountain crossing in 4 days. Traditional wagons required 6 days due to repairs and equipment failures. In frontier travel, 2 days could mean the difference between reaching destination before winter or being caught by early snows. The rain also revealed another advantage of the oil treatment. Wheels that had been oil-bathed showed no swelling or warping despite extended exposure to moisture. The oil seal prevented water absorption that caused traditional wheels to swell, distorting their shape and loosening joints. This field test under genuine frontier hardship provided undeniable evidence of method superiority. The skeptics who remained faced uncomfortable facts documented in official reports. Could the axle bath method stand up to even harsher conditions, or had it merely been fortunate in this particular test? Winter provided the most severe test of any frontier technique. A group of settlers attempting a late-season crossing of the Rockies experienced temperatures that dropped below -20 degrees Fahrenheit for extended periods. These conditions exposed the fundamental physics underlying Ward's method. Traditional grease stiffened at temperatures below 30 degrees, becoming nearly solid at lower temperatures. This solidification meant bearing surfaces received no lubrication during the coldest periods, precisely when friction from increased viscosity generated the most heat and wear. Oil-bathed hubs performed differently. The oil reservoir within the wood remained somewhat protected from extreme cold by the wood itself, which acted as insulation. As friction generated heat during wheel rotation, that heat mobilized the oil, bringing it to bearing surfaces. The thermal cycle became self-reinforcing. Cold oil was mobilized by friction-generated heat, which reduced friction, which paradoxically allowed enough friction to generate the heat needed to maintain mobility of the lubricant. The system found an equilibrium that traditional surface-applied grease could not achieve. Temperature logs maintained by a settler named Marcus Webb documented the conditions. December 15th through December 22nd. Temperatures consistently below -15 degrees. Ward method wagons continued functioning. Traditional wagons required chocking wheels at night to prevent bearing seizure. 3 traditional wagons suffered cracked hubs from thermal stress combined with bearing seizure. The cracked hubs revealed another consequence of inadequate cold weather lubrication. When bearing surfaces seized, continued rotation had to occur somewhere in the system. The stress transferred to the wood, which became brittle in extreme cold. The combination of brittleness and stress caused catastrophic failure. Oil-bathed hubs showed no cracked failures during this period. The maintained lubrication distributed stress across the entire bearing surface rather than concentrating it at failure points. This winter trial produced the most compelling statistics yet documented. During 7 days of sustained cold, wagons using the axle bath method had a failure rate of 0%. Traditional wagons had a failure rate of 28%. 15 wagons out of 53 suffered significant bearing-related damage. The data was irrefutable. The method worked under the most extreme conditions likely to be encountered on frontier trails. Would Ward's axle bath method withstand the final test of long-term durability and widespread adoption? By early 1850, enough data existed to perform rigorous economic analysis of the axle bath method. Multiple sources contributed to this analysis: trading post records, settler journals, military supply records, and commercial freight operators' account books. The numbers revealed savings that exceeded anyone's initial expectations. A typical wagon traveling from Independence, Missouri to Oregon's Willamette Valley covered approximately 2,000 miles over 4 to 5 months. Traditional maintenance consumed between 300 and 400 pounds of grease, costing approximately $12 to $15 at frontier prices. The axle bath method consumed approximately 25 gallons of tallow over the same distance, equivalent to about 180 pounds. At frontier prices, this represented a cost of approximately $7. The direct material savings, $5 to $8 per wagon. But material costs represented only a fraction of total savings. Traditional maintenance required approximately 45 minutes per day, plus major repairs averaging 6 hours per month. Total maintenance time, approximately 150 hours for a complete journey. The axle bath method required approximately 45 minutes per day, with repairs reduced by approximately 80%. Total maintenance time, approximately 95 hours for a complete journey. The saved 55 hours translated directly into additional travel, approximately 5 additional days of progress at typical speeds. Those 5 days could mean arriving before winter snows, finding better land claims, or avoiding disease outbreaks in late-season camps. Wheel replacement costs showed even more dramatic differences. Traditional wagons required an average of 2 complete wheel replacements during a full westward journey. Each replacement consumed significant spare materials and labor. The cost, approximately $25 per wagon in materials plus labor. Oil bath wagons required an average of 0 complete wheel replacements. The oil treatment preserved spokes, prevented hub cracking, and reduced axle wear to the point that original equipment survived the entire journey. Total economic advantage, approximately $40 to $50 per wagon, roughly 10% of the total cost of outfitting a family for western migration. For commercial freight operators running multiple wagons, the savings multiplied proportionally. These figures, compiled from multiple sources and preserved in various archives, demonstrated that the axle bath method was not merely technically superior, but economically transformative. The data showed that those who adopted the axle bath had fundamentally better outcomes than those who resisted. By mid-1850, the axle bath method had transitioned from individual innovation to institutional standard practice. Commercial freight operations, military supply trains, and established wagon services adopted Ward's technique as default procedure. The Russell, Majors, and Waddell Freight Company, which would later operate the Pony Express, issued internal guidelines in June 1850 mandating oil bath maintenance for all wagons in their fleet. The company operated over 3,000 wagons across western routes. Their adoption represented validation at the highest level of frontier transportation. The company's annual report documented the impact. Implementation of improved wheel maintenance procedures has reduced equipment failure rates by 63% compared to previous year operations. Maintenance costs have decreased by approximately 40%. Delivery times have improved by an average of 8 days per long-distance shipment. Military freight operations followed similar patterns. Fort Laramie's quartermaster records from summer 1850 noted, "All supply wagons now employ the oil bath technique for wheel maintenance. Significant improvements in reliability and reduced maintenance burden have been observed." The method's adoption by institutional operators accelerated its spread among individual settlers. When commercial freighters and military operations visibly employed a technique, it gained credibility that individual advocacy could never achieve. Blacksmiths at trading posts began fabricating tin troughs as standard items, selling them alongside other frontier necessities. The troughs evolved slightly. Some featured legs for easier positioning, others included simple handles for moving them while hot. The basic design remained unchanged, a rectangular vessel sized to submerge a wagon hub. Farriers and mechanics formalized the technique into teachable procedures. Apprentices learned the axle bath method as part of standard wagon maintenance training. The knowledge that had begun as one man's experimentation had become codified practice. By late 1850, the transformation was complete. What settlers had mocked 18 months earlier had become standard frontier engineering. The squeaking, grinding wagon trains that characterized Western migration in the 1840s gave way to quieter, more reliable transportation in the 1850s. The method had proven itself through every test: daily wear, extreme weather, economic analysis, institutional validation. No reasonable skepticism remained. What began as skepticism now became frontier tradition. Ward's quiet innovation had fundamentally changed how thousands of wagons moved west. The tin trough, once ridiculed as wasteful foolishness, had earned its place alongside the essential tools of frontier survival. The axle bath method sparked broader innovations in frontier mechanical maintenance. The core principle, using thermal properties and deep penetration to achieve superior lubrication, found applications beyond wagon wheels. Patent records from the 1860s document numerous adaptations. Sawmill operators adapted the technique for blade bearings. Windmill mechanics used similar approaches for gear lubrication. Mining operations employed large-scale versions for ore cart maintenance. The U.S. Patent Office recorded the first formal patent related to axle bath technology in 1862. The patent, filed by a mechanic in California, described a specialized trough with integrated heating elements and temperature regulation. The patent application explicitly referenced the widely adopted Ward method of wheel maintenance as prior art, formal recognition that the technique had become baseline knowledge. Subsequent patents refined various aspects: troughs with better drainage, oils with improved temperature stability, techniques for maintaining optimal soak temperature in varying weather conditions. Each innovation built on the foundation that Ward had established through observation and experimentation. The method influenced thinking about mechanical maintenance more broadly. Frontier engineers began understanding that preventive maintenance through proper design was superior to reactive repair of failed components. This conceptual shift affected everything from building construction to tool design. Technical manuals from the 1870s included axle bath procedures as standard content. Books on frontier mechanics, wagon maintenance, and Western travel all described the technique. What had required personal transmission through demonstration in 1849 had become documented knowledge available to anyone who could read. The economic impact extended beyond individual cost savings. Entire supply chains adjusted to the new reality. Grease production decreased as oil bath adoption increased. Tin production for troughs became a standard product line. Spare wheel manufacturing declined as wheel longevity improved. The cumulative effect was a more efficient frontier transportation system. Wagons moved faster, broke down less frequently, and lasted longer. These improvements accelerated Western settlement by reducing the barriers to long-distance migration. Ward's innovation, born from frustration with squeaking wheels and constant repairs, had contributed to reshaping the logistics of American westward expansion. The tin trough and bucket of hot oil had proven as consequential as any dramatic technological invention. What started with oiling wagon wheels eventually transformed frontier engineering across multiple domains. Eli Ward settled in Oregon's Willamette Valley in late 1849. He established a farrier business that served the growing settler community for 3 decades. He never claimed credit for revolutionizing wagon maintenance, never sought patents or financial reward for his innovation. His original logbook, preserved by descendants and later donated to the Oregon Historical Society, documents the method's origin and spread. The entries are practical and precise: dates, weather conditions, oil quantities, wheel conditions, mileage traveled. The tone throughout is matter-of-fact, showing no awareness that his notes documented something historically significant. The final entry related to the axle bath method, dated September 1849, simply stated, "The method works. Others are using it. No more squeaking wagons in camp." Good. Ward died in 1882, having lived long enough to see his technique become so universal that few people knew its origin. Younger settlers and freighters in the 1880s employed the axle bath method without knowing a specific person had invented it. It had become anonymous knowledge, passed from mechanic to apprentice, from father to son, from one wagon train to the next. This anonymity represented the highest form of success for practical innovation. The method worked so well and spread so completely that it stopped being Ward's method and simply became the right way to maintain wagon wheels. The broader lesson resonated beyond wagon maintenance. Observation, experimentation, and willingness to be mocked for trying something different had solved a problem that affected thousands of people. The solution required no rare materials, no advanced education, no institutional support, just careful attention to cause and effect. Through observation, adaptation, and knowledge sharing, frontier settlers overcame challenges, one practical innovation at a time. The axle bath method represented a small victory in the larger struggle to make the impossible journey west slightly more possible. Ward's tin trough, his heated oil, and his nightly routine had given thousands of settlers a measurable advantage. Quieter wheels, fewer repairs, lower costs, and faster travel. These concrete benefits accumulated across years and miles into something larger. A frontier made slightly more survivable through applied intelligence and shared knowledge.